All right, class, here's section 5.4. So as I mentioned in my previous video, I have posted the section 5.3, but we are really not required to cover that. I just wanted, in case you are interested in more in these Riemann sums that we're going to be talking about in a minute, I'll try and give you basically an overview of section 5.3 here. But we're not in a calculus class, so that simply means that we don't need to become or to get that technical. So I will still try and review a little bit to give you an idea of what it is we're looking for or what we're doing. And if you want to read up more about it, then you're definitely welcome to check section 5.3. Okay, so we're talking about something called definite integration. So if you remember from the last two sections that we talked about, we have computed something called an indefinite integral. So we're going to go over the two of them a little bit later in the section to find the difference between what a indefinite integral is and what's the difference to a definite integral. Okay. All right, so the story begins the same way we talked, or with the story that we discussed in really the second section of this course in 1.2, when we talked about tangent lines and slopes of tangent lines and instantaneous rates of change and how we would be able to find that. So the story begins here with the area under a curve. So we're starting with the function f of x, and let's keep it simple for now and say that f of x is a positive function. By a positive function means it's above the x-axis for now. What we want to do is we want to figure out the area under the curve, right? So how will I be able to find the area under this curve, okay? And that goes back to really being able to find area of shapes that are not regular. What do I mean by regular? We all know how to find the area of a rectangle. Yes, it's simply length times width. There's formula even for a circle, even though that's not straight-sided figure, but there have been formulas found for that as well. Well, guess where those formulas came from, but I'm just saying. But it turns out that we can find the area under an irregular shape if we know what this function is that creates that shape. So this is the idea. Remember how when we first in chapter 1 talked about how could I find the slope of the tangent line to a point, right? We can't find the slope at a point only because it's just one point, and you can't find a slope with just one point. So what we did is we picked another point close enough to this one, and we approximated the slope of the tangent line by the slope of the secant line. And we figured the closer we move the second point to my initial point, the better the approximation gets. So the same thing here. How could I figure out the area under this curve? Well, we know how to find areas of rectangles, so we can find an approximation. So what we do is we're cutting this interval from A to B into intervals of equal width, and let that width be delta x every single time. And again, how would I find this delta x? Take the whole interval from A to B, minus them in other words, right? And divide it into n equal parts. So this delta x will simply be b minus a, so whatever. If you go from 1 to 5, that's a distance of 4 units, and divided by n equal intervals, yes? Now, sure enough, again, let's look at 5.3 for more pictures, but what would make the approximation of this? And then what do? We build this rectangle, right? Find its area. Build this rectangle, find its area. Build this rectangle, find its area, and so on, yes? So sure enough, if we add up these rectangles, the areas of these rectangles where the width is delta x, The height is what? It's always given by the function value, right? So the height is the function value. So let's say, what is the height of this rectangle here? Well, f of b, right? Plug this value in into the function that gives you the height. So that's how we can figure that out. And then we can approximate the area under this whole shape by the sum of the areas of all these rectangles. Now, sure enough, there's going to be some gaps up here, yes. What would make this approximation better? Well, sure enough, the approximation will be better if we choose what? More rectangles. So think about, again, under this shape, if we pick a rectangle that's only this wide and another rectangle that's only this wide, right? So the leftover gaps under there will get smaller and smaller. So what do we want? We want this number of rectangles to be close to infinity. So if we pick infinitely many rectangles, it's almost like picking rectangles with a width of 0. So it's almost as if I'm starting to fill in this surface with a bunch of lines, right? So rectangles that are thin as lines. And then sure enough, my approximation would be nearly perfect, right? To the actual values. Okay, so the sums of these rectangles, which again are what? What did I say? How do I find the width of any rectangle? It's a delta x. How do I find the height of any rectangle? Is f of this, it's the y value, right? So if this is some xi, right? Some point in between 1 and 5, yes. And this is 4 or 4.5, whatever it is. It's a value between these two, a and b. The height of this rectangle is the function value added. So each of these rectangle has a width times a length, right, or a height. That's the area of one of them. And then the sum means I add it. This is a summation notation. Simply means that I add it to the area of the next rectangle, and so on and so on. So when is this approximation better? If we're using how many of these rectangles? Infinitely many. So if we let n be infinitely large, then the sum of the areas of these rectangles best approximate the area under the whole shape. Now, it turns out the area under the whole shape, we call it the definite integral. So it's the integral from a to b of f of x dx. Now, sure enough, you have seen this part. Integral from a to b, no, I'm sorry, integral of f of x dx. That was the indefinite integral. It turns out that they are one and the same idea. So again, the definite integral is the area between the function, the x-axis, right? So it's the area under the curve. The function f is called the integrand. A and b are called the limits of integration. All right. This elongated s comes from the summation notation. So this integral is really the sum of all these rectangles. So as I had mentioned in 5.1, it has the shape of this elongated s. Okay, that's why, from the word sum. Okay, and this integral symbol corresponds to the sum from, it's called the Riemann sum because of the guy who invented it, right, who came up with this method. Okay, now, where do you think the dx comes from finally in this notation? I said I would mention it later, now it's the time. The dx comes from the delta x, the width of these intervals, right? So that simply tells you x is the variable. X is the variable used in this function, yes? So that's where the dx morphed out of, this delta x width of intervals, yes? So that's where it comes from. Now, the point is, how do I know, right, that the area under this curve is in fact the antiderivative of this function? That is exactly the topic of the fundamental theorem of calculus, which is huge. It simply tells you the connection between a function and its derivative, and then the derivative of its antiderivative. So it turns out that, again, the integral from a to b of a function, if this is a derivative of some function, the area under the curve is the function itself, evaluated between these two limits of integration. So let me just give you an example, and I will draw it right here. Let's say, I can give you an example from physics. Sorry about that. I can give you an example from physics. Let's say this is the velocity function. We talked about velocity and acceleration. And this is the time. So this is how the speed of a car is changing in time. So let's say at 1 minute, or let's say at an hour, the car is driving at this speed, right? At 2 hours, the car is driving at this speed, and so on, and so on, and so on. Now, what would be the area of this rectangle going to mean, right? So the area of this rectangle is simply what? Each of these intervals is what? The width of the interval times the height. Now, what's the width of the interval? The time elapsed, right? Within an hour. What is the velocity that you drove for this time? Now, if you multiply, velocity is distance, right? So velocity is miles an hour, right? Time is hours. So if you multiply miles per hour times how many hours, right, you've been driving for, what you get is miles, yes? So the area under this curve is really time times rate, which is nothing else but distance. So distance is how far did you get within this period of time if you were driving at these speeds. Now, if you remember from chapter 1 that the velocity was what? Was nothing but the derivative of the distance function. So what is the area under the velocity curve? The distance. So in other words, the antiderivative of the velocity function. I can show you this again. Let's just say this problem would not be about velocity and time, but let's say this problem would be about the rate of change in the value in an account, right? So the value in an account is growing at this many dollars per year. So it would be, let's say, a velocity is a change, right? A rate is a change. So let's say this is not a velocity, but it's how many dollars per year do I make, right, in this account. And if we multiply it by what? The number of years, the time, what we get is the total amount of dollars, right, that we have created in this account. So that simply is the antiderivative, right? So I'm giving you the velocity. I'm giving you the rate of change, yes, in a function. The area under the curve is really the total accumulation in that function, right? So if it's dollars per year times number of years, so dollars per year times number of years gives you total amount of dollars gained, right, within this time elapsed. Does that make sense? Okay. All right. So that's exactly what the fundamental theorem of calculus simply says, that these two, the integral and the differential calculus, are connected in this way, that the integral from a to b of a function, so again, what I'm giving you is the derivative function, yes? The graph of the derivative. So if I'm starting with the graph of a derivative, the area under this curve between a and b is simply the accumulation in the antiderivative. So how much did you gain from this point to this point. In other words, let's say your derivative was again what? Dollars per year, yes? And you multiplied by this many years elapsed, let's say between the 5th and the 10th year of you putting in money in that account. Now what you get with the area under this curve is simply what? Whatever money you had after 10 years minus whatever money you had at 5 years. So it's the difference or the accumulated amount of money, right, between these 2 years. And that's exactly what it says here, that the integral or the definite integral from a to b of a function f of x dx is the antiderivative between a and b. So this expression here simply means between a and b. And what you get is you evaluate f of b, so the antiderivative at the, we call this the upper limit of integration, minus the antiderivative at the lower limit of integration. So it's how much did you have when you got here minus how much did you start from here. So it's the total accumulated value. Okay, so I'm going to write this down one more time, that the definite integral from a to b of f of x dx gives us the total accumulation in the function f of x, which is the antiderivative, such that what? The derivative of the original function is this f of x. So this f of x is the derivative of this capital function f of x. Okay. All right, and we're going to do a whole bunch of examples out of business and figure this part out. Okay, so this is really interesting. Should have left myself a little bit more room here, but this is what we're looking at. I'm going to prove to you that to find the area under the curve simply means to find the antiderivative and evaluate it between these two numbers. So just as we said. So it says find the area under the curve of f of x or y equals to x plus 2. There's the function between x equals to 1 and x equals to 5. So what I'm going to do is actually draw this curve. So y equals to x plus 2 is a line, right? All right. So what about this line? It has a y-intercept of 2, and it has a slope of 1. Okay. And if it just keeps going at this rate, here's your y equals to x plus 2. Okay. All right, so it goes up 1, 1. So I'm just going to do this. 1, 2, 3, 4, 5, 6, 7. That's what I'm trying to show you. That by the time, if x is 1, then that's going to be as high as 3. Yes. If x is 5, then that's going to be as high as 7, right? 7, 5 plus 2 is 7. Okay, so it's a line. So it says, find the area under the curve of y equals to x plus 2 between x equals to 1 and x equals to 5. Under the curve means all the way down to the x-axis. Okay, so how could I find this area? Well, using areas, luckily this isn't a curvy shape, but it's got straight sides. And if you look at it and kind of turn it around, this is a trapezoid, right? These two sides are parallel to each other. Okay. So the area of a trapezoid is 1/2 base 1 plus base 2 times the height, by the way. Don't need to know it because we're going to find the areas really using integrals, but that's the area of a trapezoid, is the average between the two bases times the height. So what are the two bases? Well, this base is from here to here. How many units? Well, from 0 to 3 is 3 units high, yes? The second base is this. How many units are from here to here? Well, it looks like 7 units, right? That's the y coordinate of that point there. And the height of this trapezoid is the distance from here to here, yes, between the two parallel sides. So from 1 to 5, that's a distance of 4 units. So plug that in, times 10 times 4, that's going to be 20 square units. So there's exactly 20 little squares, if you should count them, under this shape. Okay, now using integrals, this is what we've learned, that the area under the shape of some function is the integral from what to what. These are my limits in integration from 1 to 5. So I'm counting this area starting at an x of 1, ending at an x of 5 of, what's the curve? Is x plus 2, right? F of x is x plus 2, that's the function, dx. So the rule said we already learned how to find the antiderivative of this function. So it says, find the antiderivative of this function. Well, what's the antiderivative of it? X to the 1 is an x squared over 2, plus the antiderivative of 2 is 2x. Now, if we were to, and I'll show you that, if we were to just find an indefinite integral, in other words, just an antiderivative, we'd have to add a constant k there, right? But we don't do that in this case. I will show you why. Because what are we doing here? We're taking this expression and evaluating it, it says, between 1 and 5, yes? So you find the antiderivative, and then you evaluate it between these two limits of integration. Now, what does that mean? It means that you're going to plug in the 5. So 5 squared over 2 plus 2 times 5. And then you're going to plug in a 1. Okay, so that's 25 over 2 plus 10 minus 1/2, and then be careful to subtract, right? Distribute that minus 2. And then 25 over 2 minus 1/2, that's 24 over 2, by the way. 10 minus 2 is an 8. So that's a 12 plus 8 is 20. Okay. Now, did we get the same answer? Absolutely, yes. So that was the point, that we better get the same answer. Now, whether we're using geometry, yes, or we're using calculus. Now, I purposely left a little bit of a gap in there to show you this. What would be the antiderivative of this function? It had that k value in there, yes? So if I plug in the 5, of course, it's 5 squared over 2 plus 2 times 5, and there is nothing to plug into k. K is a constant, yes? Minus, plug in a 1. 1 squared over 2 plus 2 times 1, and then plus k. Now, what's going to happen to this k? I have a plus k here, and with this minus here, I have a minus k. So what's going to happen to the k's? They're going to cancel each other out every single time. Yes, it's the same k value that you plug into this number, minus the same k value that you plug in this value. Again, nothing to plug in, they're constants, yes? So there's nothing to put in there, okay? So they go away. So as you see, there is no k in this formula. Why? And I'll put it here, k cancels out. So there's no need for this k, okay? K cancels out. Okay, we're gonna stop this video here. It's getting really long, my explanations. I've explained the same thing in the textbook, so please read it. If you want to read some more about Riemann sums, do read section 5.3. Again, the hard thing about business calculus is that we don't quite do all the calculus behind. It would just take up too much time and too much building up. But I also can't just tell you that's what we're doing without really explaining to you the connection. So I'm trying to quickly give you a background idea of what is happening really in these problems, okay? Now, all we're going to do is do the mechanics, find the definite integral, find the definite integral. And I will show you in just a bit what the difference is and how do you know when to find what. But in this really long video, I still wanted to at least give you a little bit of a background of what a definite integral, where did it historically start. And by the way, also in the text, I've linked the proof to the fundamental theorem of calculus, if you're interested in looking this up.